Welcome to the AI Chat Podcast. I'm your host, Jaden Schaefer. Today on the podcast, we have the pleasure of being joined by Praneet from Google DeepMind, who's a senior research engineer, having previously worked on AI for industrial controls in its applied group. Praneet serves as part of the technical program committee for leading AI venues such as NER IPS, ICML, and ICLR. He's a member of the Confederation of Indian Industries Artificial Intelligence Task Force. Prior to DeepMind, he was a machine learning engineer at Google Cloud. Super excited to have you on the show. Welcome, Praneet.
Hey Jaden, thanks for having me on here. It's a pleasure to be here.
Like I mentioned, really excited to have you on. I would love to kind of kick this off by asking you a little bit about your background and your journey. I'm wondering if you could tell everyone a little bit like what brought you to doing what you're doing today. Was this something you always knew you were kind of interested in, machine learning and AI and all this kind of stuff? Or is this something you kind of discovered as you went along? Give us a little bit of your background.
Yeah, great question. Love to recollect the past. So I think for me, where the point at which I kind of figured out this is what I want to do was back in undergrad, and it's starting. Well, this is a while ago. I would say like 8, 9 years ago at this point, towards the end of my undergrad. Back then, we didn't really have these large language models or some of the crazy advances we're seeing today. Um, all I had was Andrew Ng's course from Stanford. It seemed pretty interesting to me. We had some stuff on like autonomous vehicles, I think, from that was just starting to pick up at that point. And I was like, okay, this is pretty cool. This does sound interesting.
Have you ever wanted to start your own podcast? I record and publish podcasts on a platform called Spotify for Podcasters, and I absolutely love it. Essentially, you can upload from your phone or computer, and it distributes to every platform that plays podcasts. They support video podcasts, and you can make money on the platform with ads or even podcast subscriptions, something that has made my life so much easier as a podcaster. So if you're interested, I highly recommend you give it a try. You can download the Spotify for Podcast app, or go to spotify.com/podcasters to get started on your podcast today.
I was in a project in undergrad where I very partially contributed on building a student race car, and that's where I saw some of the stuff which, I think CMU and Stanford were doing. And then I was like, oh, autonomous vehicles, there's this crazy thing called neural networks. Let's learn more about it, and even especially machine learning. That was interesting to me. I worked on a mini project with a few buddies. We published a very, very basic paper back then on optimizing our car's engine performance using neural networks. And we went to a conference internationally, and there we met a lot of really great academics. And I was like, oh, this is really cool. Like, to see people publish really amazing papers and doing some really cool research. And I had an intuition back then that some of the stuff we are seeing right now could be applied in so many different fields, and it could pretty much change industries. And that was kind of the seed that fell in my head. And so long story short, I came to the United States for my master's. I did a cool internship in reinforcement learning, joined Google full-time after graduating, and I've been in the Alphabet family since.
Super, super cool. Amazing background. And it's always interesting for me to hear, like what kind of got you started, what got you interested. Kicking this off, something that I hear a lot and I'd love to get your take on. I'm wondering if you can explain to the listener, what's the basic difference between reinforcement learning and just traditional machine learning? Because this is kind of where you work, right?
Yeah, that's a great question. I think for things like this, I like to go into very simple explanations, not going too deep into maths. If you think of supervised learning as, you're studying for a test, maybe like a maths test, they ask you a question, you give a response, you see the answer's wrong, and then you kind of say, oh, this is where I went wrong, you go back, right? So you have the sort of like
Yeah.
output, like a test answer, and then you go back and you solve it. Reinforcement learning is something like learning how to ride a bike, and assuming you have no one to help you, right? So the first time, and I remember my first time because I fell a lot. You go on the bike, you might, make it a foot or so, you fall down, you're like, oh, maybe I should put more pressure on one side over the other to balance myself. Then you go slightly longer, maybe you make a mistake in turning, you fall again. But iteratively over time, over these experiments for like falling, getting up, realizing what's wrong, you then manage to do much better, learning from these experiences all by yourself. And you might meet your end objective, maybe cycling from your home to your school or so forth. So I think like this is one fundamental, hopefully clear way of knowing the difference between the two. Now, if you were riding a bike and then you had your friend telling you at every step what is correct and what is incorrect, that can be considered one of the supervised learning paradigm over there.
Okay. Yeah, makes a lot of sense. Appreciate the explanation. So, something I want to ask you about, because I know you've worked in this space specifically, and I think I find it kind of fascinating, but why do you, well, like, what's the concept, but with applying reinforcement learning to commercial cooling systems? This is something that you've worked on, correct?
Yeah, great question. So, you know, reinforcement learning is something that always fascinated me since I started learning about it. We've seen it do really well in like simulated virtual environments, like in video
Hmm.
games. You've seen those nice GIFs of, those Atari games like Pong and Breakout. Does really well. Um, the real world is a lot more complex, and I can speak about that for a while with all the challenges which we faced. But there's also a lot of potential for algorithms such as reinforcement learning to optimize things such as the cooling systems of data centers, amongst others,
Yeah.
and make it perform
Okay.
well. It's quite dynamic. There's a lot of knobs which we could tweak, which think of as a human operator is a lot to keep in mind. And this is a place where reinforcement learning can come in well. It fits in the paradigm of like acting sequentially different steps towards a given goal. And,
Hmm.
and that's why we decided to start working on the project.
Okay. Super, super interesting. Um, I'm wondering if you can tell us a little bit about, some of the core components of your simulation suite that you use.
Yeah. So taking a step back, so when we decided to work on reinforcement learning for real world systems such as like massive industrial buildings, data centers, malls, um, working directly in the real world is hard, right?
Hmm.
Imagine like you apply reinforcement learning in a game, and reinforcement learning is quite sample inefficient in the sense that it takes like hundreds of thousands of iterations in some examples to actually learn a reasonable policy. And it
Hmm.
even before it learns the policy, it does things that can be considered quite wrong. So as an
Hmm.
example, if you play the game of Pong or Breakout, if you lose the game, it's fine. You just lost the game, you got a negative reward, right? In a real world
Hmm.
data center, if the reinforcement learning does something wrong, like it turns a water pump up real high or low, that can be catastrophic, right? Like it can lead to things, such as shutting down data center. So,
Right.
to kind of summarize that, like, the real world is hard because you don't have the luxury of so many interactions with the real world environment to learn a reasonable reinforcement learning policy. So interactions are limited. So we use something called offline reinforcement learning to tackle that. Um, but there are other issues as well, such as, like um, sensors. Like, as you can imagine, like in real world systems, you're quite dependent on sensors to give you an accurate reading of what's going on, how you're doing. So getting input data from those is quite time consuming as well. There's a latency aspect to it. But the sensors, they also, like all mechanical systems, they might start to drift, start telling you things which are wrong, and that adds more
Hmm.
complexity to something as sensitive as what we have as reinforcement learning here. So, taking a step back, so given all these challenges, we decided to build this suite. We called it the
Hmm.
Industrial Task Suite. And the basic idea of it was, could we quickly test out different hypotheses over here, such that we could say that if A is better than B, we don't care too much quantitatively how much difference is, but we can give an idea that if a variant of an RL agent A can perform something better than B in this environment, that should potentially translate over to the real world as well. So
Hmm.
yeah, so that's what our goal was with the suite. And as to sorry to finally answer your question, the core components which we had over here was similar to what we would see in the real world, with just swapping out a real data center with a simulated one. We built a simulation, like it's like a Microsoft flight simulator for industrial systems. We
Uh-huh.
used a software called COMSOL of a large data center that simulated the fluid flow of water through pipes, the pressure of pumps, the atmospheric conditions, and we kept it quite parameterized so we could try out many different kind of interesting scenarios of real world cases. And then with this simulation, we swapped it out with, we then connected it to a reinforcement learning framework, Acme, and then we could allow an agent to play around with a simulated version of a data center rather than a real version of it.
Super, super cool. Yeah, I love that. I think that's such a fascinating idea, and kind of creating this whole simulated environment. Something I'd love to ask you about is like, what were some of the most interesting or exciting or unexpected like takeaways while you were kind of playing with that or using that?
Yeah, there were quite a lot of interesting and exciting takeaways. I think for me, like fundamentally, I spent a lot of time like building up the actual simulation. So I was
Uh-huh.
not an expert in fluid dynamics or these multi-physics
Okay.
software. So it was quite an engineering effort, and we had some really great folks, helping us build this out. So it's a team effort. So we invested like a few quarters, kind of like setting up the base simulation. But the first time we could actually like have a simulation, then build a wrapper on top of it to like certain conditions. So like let's say a sunny day in the Bay Area with like this sort of data center, and then plug in a reinforcement learning for control. The first time we kind of saw that work out, and then saw the training loop converge towards a policy. I think that was, I think, by far the most exciting thing which I saw. Then we did a lot of other cool, interesting stuff. We applied like we had a really amazing intern work with us, and then we did something with hierarchical reinforcement learning, where we kind of like worked on longer sequence controls, which was really great. But I think the foundational, like the very first step when we got it to actually, like say hello world in a sense, that was
Uh-huh.
the most exciting for me. We did have a lot of challenges. These simulation suites are quite tricky, like especially like the multi-physics aspects of it. The
Yeah.
reinforcement learning agent, like in the real world, it could potentially blow something up, but even a simulation suite, it does something crazy. The simulation would stop, or things would get really, really bad. So there's a lot of
Hmm.
times where we have to manually intervene, set this sort of debugging pipeline up and figure out what did the agent do, go back and then try to
Hmm.
fix it and rinse and repeat. So that part at times could get a bit, engineering heavy, and it's like, oh, I'm not trained to do this, but I got to figure this stuff out as well to solve a larger problem. So yeah.
Yeah. That's so fascinating. That's so cool. What I'd love to ask you about is, like, how does the reinforcement learning control, the RL control, compare to traditional controls in energy savings?
Yeah, yeah. So based on my understanding, the way traditional these energy building management systems work is they have something called heuristic-based controls, which to make
Mhm.
a gross oversimplification, which might be incorrect, is something as simple as many nested if-else statements. So if the outside temperature is above this limit, and the inner you have like a lot of people in the building, it's a warm day, then you do a lot of cooling, right? But as I said, like this is a large state and action space in the sense that you can control a lot of knobs, such as the fluid flow, the pressure, um, as well as there's something called a cooler, which I consider the heart of the system. So you can say how hard you want it to run. So I would say in the order of the well, it depends from data center. Data center, it's definitely order of 2 or 3 digits. The state space. And the action space is also definitely more than 2 digits. So to write like a heuristic based code to control as complex as this, it's hard, it's doable. That's how
Uh-huh.
modern buildings, I assume, run, but it's not fully optimized to make things as efficient as possible, just given how complex this task is, right? The thing with reinforcement learning is while it's not explicitly controlled, it can kind of learn the way reinforcement learning works is it learns from repeated interactions with the environment. So it might look at the input sensor data and say, oh, okay, it's a warm day, so I'll just increase the cooling slightly more. And then based on whatever reward we want to optimize for, it says that, okay, cool, you did the right thing, you increased it by the right amount, so we'll give you a high reward, versus maybe not doing anything, getting a low reward. So over multiple interactions environment, the reinforcement learning, rather than like hard coding this, learns the interactions between states, actions, and rewards, and can then perform a task um, potentially better, as what we have seen in our case, than a heuristic-based control. One key point I want to make over here is like the reward
Mhm.
engineering. So in reinforcement
Okay.
learning, it could be considered potentially unstable at times. So you have to really make sure you're optimizing for what you really want, and making sure that is represented correctly.
Okay. Yeah. No, that makes a lot of sense, and I think that is a great point. I'm wondering, how does your system adapt to real world industrial changes? Because inevitably those happen, right?
Yeah, yeah. So I think one thing which we have seen, and like this is what we tried in the simulator a lot. The end goal for us with the simulator was to have this sort of like sim to real component, which unfortunately, at least I was not able to do. But in the real world, what we see is that well, I guess we didn't see a large change in like the control input. So you kind of control
Mhm.
the same things, but you have like different patterns. So you have like weather patterns. So you have like
Hmm.
daily patterns, like day and night cycles, but you have like even lower frequency patterns, like the seasonal patterns, and then like climate change over the years. So every year is maybe relatively warmer than the year before. So those kind of things, the outside temperature, humidity, all of these affect the amount of cooling you need in the building, and as a byproduct of that, how much cooling these chillers or your air conditioners need to produce, right? Um, you have other sort of patterns as well that also affect it. You have like the building load. So, for example, in commercial offices, you have more people in the building during the day and less at night, and same. And the opposite for residential buildings. Well, I don't know how work from home changes that, but most people are in the house like throughout the night, and then they go to office. So that also affects the amount of load which the building actually draws, right?
Hmm.
So with this, so all of this is to say that these can all be considered as like inputs to the system that affects the amount of cooling load. There's a term for that. I think it's in a unit called BTUs. And the reinforcement learning or whatever control system you have has to basically change the control inputs, or in the very oversimplified case is that if you have an air conditioner knob on how hard you want to tune it, you want to be tuning it proportionate to how much this load is changing, and that
Mm.
gets pretty tricky. And to kind of complicate that, so I told you the base cases, we also have things like
Yeah.
sensors that start failing. So, it might be a hot day and then suddenly it's cold and you're like, really, is it cold? But it's actually a sensor that just stopped working, right? So you
Oh
have
no.
yeah, so you kind of have like sensors that fail, sensors that drift. These are real world phenomenon, and these are also things that you need to take into account when a system like this. So yeah, the agent has to like kind of figure out, like, also think and plan for these more longer term patterns as
Yeah.
well.
Yeah, that's so interesting. Yeah, some of those challenges are definitely, I'm sure, tricky to solve. You guys have been doing some incredible work over there. I'm wondering, where do you see the future of reinforcement learning in energy optimization, like in going forward?
Yeah, so I definitely think there's like a lot of potential in this space. There are tons of organizations that are like tackling this. Um, I feel like and I feel like there are many other verticals as well, not just in data center cooling, right? I mean, there was a paper
Right.
out by a group on, like, I think in tokamak control. There's a paper by DeepMind, and then there are other people also using it in like other real world applications. There's a cool paper out on like drone control as well, that came out in
Oh,
Nature recently.
interesting.
Yeah, I think it was by
Okay.
the Paris University in Europe. So there's a lot of real world applications of reinforcement learning, in like robotics, industrial systems, medicine as well. So if you go all the way there. So I think that's great. Um, for our specific, for the kind of stuff which, I kind of dealt with, I feel like there are a few challenges that are, quite interesting that need to kind of be looked at slightly more deeply. And a lot of research groups are looking at it before this can be more widely adopted.
Uh-huh.
Number one, I'm not sure how many people will disagree with me on this, but we used a simulation-based approach, and the sort of end goal was like take something trained on the simulation, adapt it to real world. The tricky bit with that is something called the sim to real gap. And that basically means that something in the simulation might not adapt as well to the real world. Um,
Hmm.
and that kind of makes sense, right? Because the simulation, like, we try to keep it as high fidelity, matching the real world as possible, but even then, it misses out so many of the elements of the real world, such that, like, you might need, even if you train something really well in simulation, it might not generalize as well to a different facility.
Okay.
This is a common problem which I've seen in like the overall robotics and control space. People have spoken about this quite a bit. So I guess like this is something which more research needs to, get into this before it can be more widely adopted.
Okay.
Um,
Yeah.
sorry, one, yeah,
Oh no, yeah, no, that makes a lot of sense. That's
yeah.
super super interesting. I'm wondering, so you've obviously been kind of working in these areas specifically, but are there other industrial sectors that you think are, ready for some reinforcement learning innovation to kind of come in and make some big impacts?
Yeah, I think there are quite a few. Like, I mean, the way I think of it is like, think of tasks that are, quite, unoptimized, as they're like designed by heuristic policy, which is quite hard for like, humans to actually design. And when you have the sequential decision making kind of process, that's somewhere we can consider using something like reinforcement learning based approaches, right? As I mentioned, this is like this really cool drone racing application where people are trying to see how fast you can race drones. That's cool. There's a data center cooling process. I think there's work in um, yeah, there's a lot of stuff in like robotic manipulation, like in warehouses, like having these. I'm not sure if they use a purely RL based policy or something, or like a supervised behavioral cloning policy, which is slightly different.
Mhm.
But you have these robotic kind of bots that can help place. I'm not sure if Amazon, uh, I'm not sure if it's Amazon, but some company I know is doing something like that. Um, and in other industrial applications, well, I mean, I can't recollect off the top of my head, but I'm pretty sure if you have
Yeah.
a sort of framework, you have like a baseline that is good, but maybe not as great. And then you
Uh-huh.
can find a sort of like simulation proxy or a very efficient algorithm to learn fast in the real world. It'll be pretty cool to try out like a deep RL based solution and, kind of see how well it does.
Yeah, so interesting. Yeah, of course, there's so many applications. It's hard to come up with all of them off the top of your head. But
Yeah.
like, it's phenomenal what this is going to be applied to. I'm wondering, as we kind of wrap up this interview, I'd love to ask you, for people listening, what resources would you recommend to people that are wanting to explore reinforcement learning in their industry?
Okay, so I think this is the best part, right? Like there's like so much out there with the internet. Like I think the issue is more like just sticking to one plan and not like figuring out should I study from this or the other. Okay, so I guess like we can tackle this part in layers. Before jumping to reinforcement learning, you're not going to be in for a fun time if you don't understand the basics. And by the
Hmm.
basics, I mean things like linear algebra, probability theory, I guess the basics of machine learning, like how optimizations and objective. Well, I guess that part's maybe not as necessary. But yeah, having a very solid footing in like basic probability theory and statistics, linear algebra, that is something I would recommend. For things like those, there are many courses on Coursera, there are many books available. Honestly, there's a lot going on there. Once someone's mastered that, I would then recommend reading some literature on this. One book I do recommend is Sutton and Barto. That is considered something, I would consider it part of my curriculum for reinforcement learning.
Okay.
I think DeepMind and Google also have a bunch of talks, and other places as well have a bunch of really great talks on Coursera and like on YouTube as well that goes to different parts of reinforcement learning. Um, One thing I would say is like reinforcement learning was there before the deep learning kind of boom. So we had like DQN come out for DeepMind, but before that we had like tabular Q learning that was
Okay.
there for a while. So like most of these curriculum, I think might start off with the basics, which is what I recommend. So like the basic, value and policy iteration based techniques. And then once you have a firm footing of how those work, then they talk about how neural networks can kind of approximate how these work at scale with large state spaces, and then from there you can move on to like some of the really advanced policy optimization based techniques we use today. For example, like PPO is used for RLHF in large language models right now. So you can see how reinforcement learning is used in vastly different fields as well.
Okay, super, super cool. I really appreciate you sharing all of those resources. There's so much out there. Praneet, if people are interested in, following along with some of the research you're doing or things that you're looking at, what's the best way for them to follow you and find you and what you're kind of working on?
Yeah, good question. So I am reasonably active on LinkedIn. I try to post all of the stuff which I do.
Okay.
I try to post it over there. Um, yeah, I would say LinkedIn's your best bet. I am also on Twitter, so I assume you like link all of this there, but I kind of like also maybe put my thoughts on different papers or cool stuff happening on in this field. Fun side fact, if you like planes, and I keep mentioning that example of drone racing, I am getting in the process of, well, at least trying to get my pilot's license. So I
So
do have
cool.
an Instagram page for that if you and if your followers want to like look into Bay Area
Yeah.
flight views. Yeah.
Very cool. Well, I can leave links in the description in the show notes for people to find you everywhere. I think I'm gonna be following you on Instagram and following along on the plane journey, of course, but also on the LinkedIn and the Twitter side to see some of the cool projects you're working on. Praneet, thank you so much for coming on the show today. You shared so many incredible insights. This has been a ton of fun, a great conversation. To the listener, thank you so much for tuning in to the AI Chat podcast. Make sure to rate us wherever you get your podcasts, and I hope that you have a wonderful rest of your day.
Thank you. Thank you, Jaden. Thank you, everyone.